So continuing with our ideas on strong and weak acids and strong and weak bases, here's an example involving a weak base. Just wanted to make sure you guys were comfortable with it. So typically weak bases are going to react with water to produce OH minus ions and whatever the cation is. In this case, we're going to use ammonia. That's kind of our go-to base that is weak. So Kb, and this is just a coincidence, has a ionization constant of 1.8 times 10 to the negative fifth for ammonia. I know it's the same number as acetic acid. It is a complete coincidence. Every acid and base have their own unique numbers. So again, the first thing you're going to want to do is solve the ice chart. So we know initial concentrations. Change is going to be minus x, x, and x. Because as much of this as reacts will produce equal quantities of the two ions in the end. So equilibrium is going to be the concentration minus x, x and x. Put those into an equilibrium expression. And again, you can keep the x in there or eliminate it to make it easier on yourself. Made this slide before we got used to using the calculators in solve function. So I'm eliminating that minus x here in order to solve it. I wind up with an OH minus concentration of 4.2 times 10 to the negative 4. And so if you think about it, if that's my x, 0.01 minus that number is still essentially 0.01. So that approximation works just fine. So now that only gets me to the OH minus concentration. So we need to still calculate the pH. So if that's OH minus, I do the negative log in order to get pOH. That gives me a 3.37. And I have to go one more step. Don't stop here. Got to go one more step. I got to get the pH, not the pOH. So I'm going to subtract that value from 14. And I wind up with a pH of 10.63. That works because remember I'm dealing with a base. So use common sense. If you get this number with a base, a pH of 3 implies an acid. You've done something wrong or you haven't finished the work yet. So use common sense when you're dealing with this stuff. Okay, a couple more ideas involving weak and strong acids and bases. Percent dissociation, remember that you can calculate that by taking the amount that dissociates divided by what you started with times 100. Just a note here that percent dissociation is going to actually decrease as the concentration of the acid increases. Next idea, polyprotic acids. We don't typically have polyprotic bases or polyhydroxyl bases unless they're strong, so 100% dissociation anyway. But for polyprotic acids, there's a lot of them that are weak. And so you got to remember that each hydrogen ion comes off independent of the others. So the number of dissociation equations that you need to write are equal to the number of hydrogens that can be lost. So for example, you've got hydrogen sulfite, not sulfate, sulfite, so sulfurous acid. The first hydrogen comes off relatively easily. Notice that the Ka is 1.7 times 10 to the negative 2. But then that leaves me with this hydrogen sulfite ion. And so it too could lose an H, but notice that its H comes off in this kind of dissociation much less readily. So the amount of H plus that I wind up with is essentially due to just this H plus. A very tiny amount is due to that second H plus. In addition, each subsequent hydrogen is lost at a lower percentage than the previous, just like we saw there. If you have 3, for example, phosphoric acid, look at the Ka for the third H, 4.2 times 10 to the negative 13. You essentially have no third hydrogen being produced. So the amount of PO4 minus ions that are around is pretty much negligible. So if you have to calculate the concentration with a polyprotic acid, technically it's going to involve 2 or more ice charts. So the H plus at equilibrium from the first dissociation is going to be the initial starting concentration for the second dissociation, and so forth. There's a nice example in your textbook on page 614, on page 695, example 614, deals with calculating the H plus of a polyprotic acid. For the most part, you're going to see that those second and even third hydrogens don't contribute a whole lot to the H plus concentration. But you would still have to verify that. Last idea that I want this video to cover is a review of what we talked about earlier, the relationship between Ka and Kb and Kw. And so for acids and their conjugates, or bases and their conjugates, the Ka times the Kb is equal to the Kw. So as the strength of the acid gets bigger, the strength of the conjugate goes down because they have to multiply out always to give you 1 times 10 to the negative 14. Other idea, if we turn these all into p-values, the pKa plus the pKb is equal to the pKw, and that equals 14. Both of these ideas are going to have a reasonably important role in making titration calculations a little bit easier on you. So keep that in mind. But be very careful. Don't mistake pKa for the pH. This is the negative log of the Ka, not the negative log of the H plus concentration. So be careful not to make that mistake. pH is not the same as pKa. So here's an example. So for an acid, H2SO3, remember we said that it's weak, so it establishes equilibrium. So here is the acid, and then here is its conjugate base. So what'll happen? You'll take a Ka value for the acid, so the 2 ions are going to go in the numerator, and the acid itself is going to go in the denominator. Now, for Kb, the conjugate, the Kb of this conjugate, so this guy accepting an H+. So the acid loses, the base accepts. So this guy accepting an H+, here's the reaction that's going to take place in that case. You've got HSO3 minus combining with a water molecule to give you H2SO3, so you're going back to this guy, and you would have OH minus ions around. So this is this guy acting as a base. So the conjugate to the acid is acting like a base, making the OH minus concentration go up. So the Kb would be the ions in the numerator, the base in this case in the denominator. So remember that we said Ka times Kb equals Kw. So here's the proof. Ka times Kb. So I'm taking these guys, here they are, taking these guys, here they are, multiplying them together, look what happens. The HSO3 minus ion cancels, the H2SO3 formula cancels. What am I left with? H3O plus, OH minus, that's Kw. These two multiplied together give me Kw. So that's why Ka times Kb equals Kw, because they're really the reverse of each other. Okay, so off you go to work on some stuff with weak acids and bases. Make sure you get comfortable with this information because it's only going to help you when we start hitting titrations.